It is my pleasure to introduce our next speaker, Patrick Shipman from the University of Arizona. The title of his talk is Pattern Forming Partial Differential Equations Applied to Optimal Packing Problems. Patrick.
Yeah, thank you, and good day. And what I'd like to talk about is partially old work with Alan Newell from quite some years ago that I did with him when I was a student at the University of Arizona, but recently been applying the similar types of ideas with Xishan Chuang to more general problems in optimal packing. So apologies to those who've heard part of this talk at least before at the EMS meeting, but I didn't make as much progress as I hoped, but so it'll be a lot of the same ideas. But what I'll do is introduce first two packing problems. One is a classic problem, that of phyllotaxis, the arrangement of leaves on plants. And then another problem is classic problem, the Thomson problem, and that's repelling particles on a sphere is the typical way of phrasing it. And our approach is to find solutions to these problems through pattern-forming partial differential equations. So I'll introduce that idea in general and then combine all of these pieces. So the idea is this will be, so the Thomson problem is normally approached via dynamical system for n particles on a sphere. And the idea is to kind of replace this by this infinite dimensional PDE, from which we can do some different sorts of analytics. Okie doke. So first, phyllotaxis problem. And just to say what the problem is and give some context for it, this is a sunflower seed head. And it's a lot of observations you can make about it, but just want to make one observation at the moment. And that is that these seeds are shaped as diamonds and roughly the same shape throughout the seed head. So the seed that's way out at this corner at the edge is pretty much the same diamond that's near the center. Now they might change a little bit in shape and size in this particular example, but the idea for the kind of the ideal case is that we think of this at the moment as a uniform distribution of these diamonds throughout this disk. And connected with that is some classic observations going back millennia concerning the spirals and the angles between the positions of these seeds. And the idea that what we observe here is quite general, even if it's not diamonds on a sunflower seed head, that the same kinds of spiral structures appear in plants, whether it be leaves or flowers and various sorts of structures. So I'll get back a little bit to that. But I just want to point out some observations that are to be explained beyond those just ideas of spirals and the Fibonacci numbers and all that come up from that. But the observation that we'll be coming back to that I want to point out now is a interplay or a going back and forth between two sorts of local lattice structure. And if you take these cutouts at the positions I marked as capital A, B, and C, those squares, and just look locally at how the diamonds are positioned relative to each other. So the cutouts are here in the middle. And what we notice is that the local lattice structure is that of a hexagon, roughly, up here at A. That's also true at C. So in general, at this radius where the cutout A was taken, the local lattice structure is roughly that of a hexagon. At the radius where the cutout C was taken, it's locally that of a hexagon. However, in the middle, that's modulated by a local lattice structure that's a square, and in between, it's some other local lattice structure. It's a little more complicated than that. It depends where you are in angle and well, but that's roughly the idea. And so somehow this, we have a lot of things coming together here. We have the idea of the diamond. There's even a shape of it, and it's not just the diamond. It has a three-dimensional shape, which we might want to understand. But there's a lot of classic mathematics there, isn't there? There's the Fibonacci numbers, which I haven't talked about yet, but kind of a classic thing, which we'll come back to that. Okie doke. But one way of saying that, one way of just describing what's here is that perhaps we have a problem of optimal packing. Namely, we take one diamond shape and we place it around this on this disk in a way that there are not many gaps between the diamonds. So we've in a way tiled this disk by that particular diamond. And of course, you can just imagine tiling a disk or any just the plane by diamonds in a way that's perfect. But somehow, okay, this plant is chosen a different way, which might not be quite as ideal. We'll come back to that. But in every case, it's some optimal packing in some sense. What I want to point out too is that this is not, well, so often the correspondence between the positions of the seeds in this case and their shapes is described by, okay, it's the positions that is of primary importance. So by positions, I mean just the centers of each of these diamonds and the local lattice structure, the hexagons or squares. And then the shape just kind of follows, like you'll form a little bulge and then those bulges will grow and bump into each other and you'll form these diamonds. But if you think of it that way, you would expect to find structures that may be more resembling a Voronoi diagram. In other words, you take each of these centers of these seeds, these white dots, and you just draw the Voronoi diagram for that set of points. And what you don't get is the diamond structure that we see. It's it's actually quite nice in a different way. It shows the hexagonal structure where you have hexagons and more the square structure where you see the squares, but you don't get this uniform packing by these uniform shapes. Okie doke. So we want to combine the more classical question of the positions of these seeds with the question of what is their shape. And this is the diagram then we'll be trying to form, and it'll be formed through a combination of thinking about some pattern forming partial differential equations that might be underlying this, but it'll give us some geometric way of putting down diamonds in a way that's not quite, there's still gaps here, but it's pretty much a nice optimal packing compared to other packings. Okay, so we'll come back to that. That's the first motivation. The second motivation is another classic packing problem that it's called the Thompson problem. And here it is. We have a sphere and endpoints. We get to place endpoints on the sphere to minimize a certain energy. So you might think minimize kind of the overall distance between the points. But explicitly what you can do is, so what you're taking is look at the distance between any two pairs of points and think of them as repelling each other, maybe as they're electrons on the sphere and they're repelling each other. So there might be a Coulomb potential. So you're summing up 1 over the distance between the points, and you could take a power of those distances as well. Okay, so that's the classic Thompson problem. And the interesting thing about it is that although you can do numerical simulations and get the solutions for any reasonable value of number of points as you like, it's only known by proof what the solutions are, the minimizing solutions or the optimal solutions for these 6 cases, n equals 2, 3, 4, 5, 6, and 12. So you might get a Platonic solid or just 2 antipodal points, but otherwise it's a hard problem to solve, say exactly what the solution is. The example here where there's a related problem called the Themis problem, and that's really the same setup, except in this potential here we're taking 1 over the radius to infinity power, so that's equivalent to just asking that you want to maximize the minimum distance between any 2 points. So you place these endpoints on the sphere and you want the minimum distance between any 2 points to be maximized. Okay, so we'll come back to both of these problems in our discussion, particularly Thomas problem though. So this will be example maybe of the Themis problem. So the idea of the Themis problem is you place these endpoints on the sphere and then you draw disks around them. So think of small disks, and then you increase the radius until the first two disks hit, and then you stop, and that's the radius that you get to put onto your spheres. And when you do that, not all the sphere is covered by those disks. And your question is, well, the other way of phrasing this problem then is, how do you maximize the coverage of this sphere by the disks? Now, this is a bit of a preview. So what we'll be doing is to solve some partial differential equation. In this case, it's done on the plane, so on a periodic boundary conditions, but on a square. And so I'll say more about the partial differential equations. But to go back to what we were seeing on the plant, we get this local hexagonal structure, say, which is kind of the optimal packing actually on a plane. And what we can do to think of this solution, so if you solve a partial differential equation, you're going to get a function in spatial coordinates x and y, and then be a function of time, but you'll come to some steady state solution. And that's what I'm plotting here. And it is locally some hexagonal structure. It has defects. It's not totally, there's some defects there. But then you can ask, well, what is your packing? So you can find the positions of the centers of these. So we have yellow here. This is the maxima of the surface. Blue is the minima. And so you can find the maxima of these points, and then you can use that as your set of points to ask what is the Thémis or the Thomson energy, or what is the packing by disks that you get corresponding to that set of points. Okay. So with those two problems, those are the problems we'd like to solve in some sense. And I'll come back then to a general introduction to pattern forming partial differential equations and why you might think of these as connected to this set of these two problems. So this is a bit of a general discussion or overview of pattern formation in general, which I think is kind of fun. What I've taken here is just a bunch of images, and all right, might not be maybe I should work on these images, but the idea is supposed to be that if you say, look at this and you see locally some nice hexagonal structure, there's some surface there. And you look over here and you see some nice hexagonal structure. And just given those pictures that I've put for you here, these cutouts, and all right, I could make them look more similar, but these two in particular maybe look quite similar, don't they? You might not know right now, what are they? Where do they come from? What's the mechanism behind their formation? I mean, these are real pictures of real physical systems. So I can put them in color, and that might give you a little bit of a clue, but that's not really the point. But now I can show you exactly what they're from. And maybe seeing our classic example here, the one on the lower right was from a biological system, and the one on the middle up there is it's a ferrofluid. So this group has a ferrofluid, so it's a magnetically responsive fluid. They put it on a magnetic field and it forms that structure. So completely different underlying mechanisms, and but a similar sort of macroscopic pattern that you see. And so you can see that in many different ways, sort of similar hexagonal patterns. This is just the collage. And again, you can imagine that, this plant here, or this mollusk there, its mechanism formation, its history is very different than, say, these water waves or something like that. And just to then give some examples of models that relate to all of this, I've made a little bit of a collection here of models, then their simulations that also give similar structures in the end. So this is a model from, I forgot I was going to put all the the references are underneath the picture. So this is an integral differential equation. It gives rise to some pattern that's undistinguishable maybe from just how we plotted it in different colors from some of the other patterns on this example. Here I've plotted Swift-Hohenberg equation, which will be relevant to us in a few moments. And there's all kinds of different equations. When you look at these, you'll see some similarities. There's fourth order terms. There's all of these equations involve some field for two spatial variables and time. and perhaps coupled systems with other variables as well. But the point here is not to look at the models and their details. The point is that they look quite different, but they produce very similar results. Okay, so, but also just to say that, well, there's a large class of systems that form patterns that have some underlying mathematical similarities. And our goal is to then use some of their characteristics to come back to the original problem of the day, which is these optimal packing problems. And in particular for that, I'd like to introduce the key equation of the day, not necessarily the equation that I'm just, all right, one example for today. So not necessarily an example that's best for the optimal packing problem you want to get to, but it's a classic problem from pattern formation models. And nice one to start with to explore the question of the day, which is, can we solve optimal packing problems using these partial differential equations? So the Swift-Hohenberg equation is a fourth order differential equation. Hope the notation is reasonably relevant here. So that's the Laplacian. You square it, so it's a fourth order equation. And Swift-Hohenberg equation typically is usually without that quadratic term, but it's important for us, for the hexagons we want to achieve, for that quadratic term to be there. Okay, so it's a variational equation. In any case, that's what it is. And it was actually the equation that we simulated in the previous slide to achieve the pattern on the left there that we described using the Themis idea. Okie doke. So actually, let's then maybe explore more the potential relationship between these partial differential equations and these ideas of optimal packing. So what we've done here is to take a time series of, so solve the Swift-Hohenberg equation. I've plotted the solution in an increasing time along these axes. And then also over time, so over time, what will happen is that these maxima will emerge, they'll merge, defects will form, defects will be taken away. And you can ask a lot of questions like, what do you do to these equations to remove defects and optimize certain properties, say, of the solution that you want to get? And the property for our case is packing in some sense. So I've looked here then at the packing, and this is actually the Themis packing. So it's the, actually it's, yeah, so what I've plotted here, should have labeled axis, but this is time. And it's what I've plotted on the vertical axis is the packing that you get if you follow this procedure that we noted earlier, which is I'm going to take the solution that we get, I'm going to find the local maxima, all of them, use those as the points, find then the packing that you get if you were to find the disk of maximum radius that you can place around all these points, and so that there's no overlap. So it's solving the Themis problem and then looking at the percentage of the square that's covered by those disks. And what you get up here is you start at 0.6, 60 sort of percent. I mean, it would have been way lower earlier in the simulation. And we achieved some packing of like 82% or so in this particular simulation. Okay. Now, Swift-Hohenberg equation, at least the simulated here, is not very good at getting rid of some of these defects. And so one interesting question, which I won't dwell on today, but is partially behind a lot of these things, is what kinds of equations amongst this whole zoo of equations that we had here could you use to really release defects most easily? And if so, suppose in a system you actually didn't want defects, what kinds of terms and what combinations of terms, even though these equations look locally the same and you get local hexagonal pattern, how can you get rid of defects? So that's a question of interest, which I won't, which is kind of motivated coming back to this problem after many years. But I just want to look at this at a high level today. Now the question would be, so here is all I'll get around to today is just kind of exploring a little bit the preliminary work to connect partial differential equations with these packing problems. But so one thing we can do is just to say, let's look at the Thomson problem and say, okay, let's take Swift-Hohenberg, for example. That's our prototypical pattern forming PDE. Let's simulate Swift-Hohenberg on a sphere. So just basically replace the Laplacian by the spherical Laplacian and related ideas. and see what happens. So on the left here is a simulation of Swift-Hohenberg on the sphere. And we play our same procedure. We look then at the maxima of the surface, local maxima. Use that as the set of points of interest then, and ask ourselves, how does this relate then to solving the Thomson or the Voronoi or the Themis problem over time? Our original goal, I thought it would get solutions to the Themis problem. But if you look at this, and this is quite consistent. Actually, I'm first just going to give some examples for fun. So what I've done here is taken the simulation on the sphere, and then in red are the local maxima. Red and blue label local maxima, and then put the Voronoi diagram around that. And the reason there's red and blue points is labeled the Voronoi positions where you get pentagons with blue, and the other ones in red. Those are mostly hexagons. So we can try this for certain numbers of points. So here is N, capital N, the number of points is 32. Here it's 43. And so I'll just for fun put up different examples here, 50. So you get the point here is that you get some distribution of points, and it's looking like a pretty even, nice distribution. So your question could be, again, how does this relate in general to the Thomson or Themis problems, for example? Okay, so in this example, then I've given just the first result here, which is one example here, and one can then go in and actually compare the Thomson energy with the Swift-Hohenberg energy. But in, oh boy, one of these colors, red actually, would be a Thomson solution to the, a solution to the Thomson problem. And I thought I'd put the number of points here. I think it's 50. Yeah, it is 50. It's supposed to relate to this last graph here, which is 50 points. It looks like it's not well graphed. It looks like just a bunch of points in the disk, but some of these points on the back of the sphere, somewhere on the front of the sphere. So these are points arranged all around on a sphere. So in red again are solutions to the Thomson problem, and in blue is a solution to the Swift-Hohenberg problem. So the point here, just numerical example, is that the Thomson problem in general, or the Swift-Hohenberg solutions in general, relate to the Thomson problem with alpha equals 1, so like the Coulomb potential. And that's a pretty general, just doing a bunch of numerical simulations, the relationship between the two. And one can compare the energy evolutions over time as well. So this is just like a steady state solution. Like run Thomson, run Swift-Hohenberg, and see their simulations at the end. But one can compare these over time as well. This is just a numerical comparison. And then the natural thing to do would be to come back and note that, hey, actually Swift-Hohenberg is a variational equation. There's energy associated to it. Can we relate that to the Thomson energy? And you can, but it takes a little bit, and that's not where I wanted to go today. The more interesting questions at the moment actually are, I think that well, in the plane or on different sorts of manifold, you can consider the same question. And it's quite interesting, actually. Swift-Hohenberg is very bad at getting rid defects. So on the plane, actually, Swift-Hohenberg does not solve the Thomson or Themis problem very easily. You need other equations with other terms. So the question is, what form of the PDE actually relates most to the problem of optimal packing? And that's close to the end. So maybe that's all. There was just the ideas there I wanted to get across. Maybe the main idea is that you can actually relate Swift-Hohenberg equation to the Thomson problem, classic Thomson problem. Since there were a lot of nice talks yesterday about Fibonacci equations and all, Fibonacci numbers, or Virahunka numbers, as we learned yesterday, I thought maybe, well, let's see, it's a few minutes left. Maybe I'll just give a very brief idea of what's related to the Phyllotaxis problem here. It's an older problem that I've worked on, but still some open questions there which relate to the idea of optimal packing and motivated the idea to look at Thomson versus Swift-Hohenberg energy. And so just to state the classic idea, and that's that if you were to take, in this case, a sunflower, and again, we get it's a more square-shaped bract here rather than diamond. But they come naturally in spirals. So if you connect bracts that touch each other and count them, in this case, you see 8 counterclockwise spirals, 13 clockwise spirals. So people from Kepler back to the Egyptians, back probably all kinds of things in history that we don't know about have noted this and wondered why they come in the Fibonacci or Virahanka sequence. Typically, so there was a little survey done once and said 95% of plants do that. So let's see, why am I doing this related to our optimal packing problem? I just want to maybe briefly say that, okay, if you were to take the positions of the bracts or the positions on the sunflower and you were to describe them in the way that we described all of our problems so far, which is just to do a disk packing, just to say what percentage of the area is covered by the disks. Then for this Fibonacci positioning of the bracts, you'll get a packing fraction of about 0.6932. And that's okay, but it's, it's a D. It's not even a C, maybe if you round it up. And so the idea would be, okay, I mean, you can form models for these, for why you actually form some pattern-forming differential equations, for why you actually form these patterns on plants. But the key idea here is behind all of these models. I tried to motivate earlier that all of these models there's some sort of general formulation behind them. And the idea is that how do you form hexagons? You form hexagons by superposition of, let's just say we did a Fourier decomposition of our surface. What we would see is 3 modes, periodic modes going in 3 different directions. Their wave vectors are described by the directions that the modes are going, perpendicular to the ripples. If you add them together, you get the hexagonal structure. But the key idea is that you can't just add together 3 and then random 3 modes. There's a relationship here, which is that the mode wave vectors have that Fibonacci relationship that is key to what we're doing. All right, so that's a very brief overview of what where Fibonacci comes in there. But the idea is that you can use that, sort of pull out of the PDE and the solution that you get, just how should you position your squares or hexagons or diamonds in a way. So you need to describe their positions, their rotations, their relative rotations to each other in order to pack this sphere or this disk, say. And you get a better packing then if you were to do that, 0.8384 compared to this circle packing. Obviously, you have a different shape here that can cover more of the surface. Now, I don't know for sure. I mean, it's hard to even totally phrase this problem, but the question is then still kind of an open question. What is the actual optimal positioning and rotation of all these elements to pack the disk? But I'm sorry, I've gone almost to the end there. So I'm going to end there. There's a lot we can say here. So the idea is what you'd want to do is actually pull this. What we did actually is to pull those rotations out of the proportional differential equations to determine how this should be positioned. But I'll end there and thank you very much.
Thank you. Is there any question to the speaker? So there is no question. Let us thank the speaker again. So our next talk will start in 2 minutes.
And thank you all. And I'm trying to figure out how to unshare my screen.